By this point, we know that a function is a relationship that takes an input to produce a predictable output. And we know that a particular type of function is the linear function. How do we tell whether a function is linear or not? A lot of what we've learned so far only applies to linear functions, but that doesn't make sense unless we're certain what we're dealing with really is a linear function. Well, that's what we're looking at today. How can we tell that a function really is linear so that we can do linear related things to it? So firstly, a nonlinear function is probably exactly what you think it is from its name. It's a function which is not a linear function. So every function is one of two. It is linear or nonlinear. Now, determining which of the two it is can be used, well, depends on the form that we have to represent the function. Now, we already know some things about linear functions, so let's state what those things are. For linear functions, we know that it can be written in our general form, y equals mx plus b. Now, just because a function isn't written like this doesn't mean it's nonlinear, but if we can find a way to write it like this, it should be linear. A table, well, the way we tested whether it was linear, the way we defined it, was whether it had a constant rate of change. We know with a linear function we can choose any pairs of entries in our table, find the rate of change, and we should always get the same thing. That's not true for nonlinear. For a plot, which is just another name for a graph, it needs to produce a straight line. If you remember, that's where the name linear function comes from. These are graphs of straight lines. Now, nonlinear functions are exactly the opposite of this. So a nonlinear function, no matter how hard you try, you won't be able to write it using our general form for a linear function, y equals mx plus b. For the table, we won't have that constant rate of change. And that's not saying you won't have some entries of the table where the rate of change stays the same. But if you check every change between every pair of entries, there will be some differences. And finally, probably the most obvious one, it's not a straight line. So when you plot the function on a graph, you won't get a straight line. Now, there are nonlinear functions which have part of their graph forming a straight line, but you won't have just one straight line forming the entire function. Okay, let's put this to the test. We're going to look at two different functions here. Probably predictably, one's going to be linear and one's going to be non-linear, but let's try and spoil the results too much, although I kind of just have. We're going to test these and see if they really are linear or non-linear using those tests that we came up with in this table. So, if we have the rule y equals negative 3 over 2, and then in parentheses x plus 4, and then plus 11, does this represent a linear function? Now, the issue that we have right from the off is that this is not in the form y equals mx plus b. But remember, the test isn't that it is y equals mx plus b, it's that it can be written as y equals mx plus b. And in fact, for this rule, what we might want to do first is see if we can simplify this a bit. Well, if I distribute here, I won't have these parentheses anymore, so that seems like it'll be simpler. So that will be negative 3 over 2 times x, Now, negative times a positive is negative. 3 over 2 times 4 is the same as 3 times 4 to get 12, divided by 2 is 6. And then we have plus 11. That's not distributed because it wasn't in the parentheses. And finally, we can combine like terms here with my constant terms to get negative 3 over 2x. Negative 6 plus 11 is 5. So that's plus 5. And what do you know? This is in the form y equals mx plus b. M is negative 3 halves and b is 5. So this is in the form y equals mx plus b, which means the function is linear. Okay, let's fill out the next example. Well, the next part of the example. So we're still working with the same function, and well, we kind of know the answer. We already know that it's linear, but let's suppose we didn't figure it out using the rule. How could we figure it out using the table? So the first step is to fill out the table. So if x is negative 4, we'll have negative 4 plus 4 is 0. Negative 3 over 2 times 0 is still 0. Plus 11 means we get 11. If x is 0, we get 4 in the parentheses here. Negative 3 over 2 times 0 plus 4, negative 6 plus 11 is 5. Let's pretend we've gone through the work to evaluate for the other ones, but these are the results that we get. Now, we need to find our changes for this table. So to go from negative 4 to 0, we are adding 4. From 0 to 2, we're adding 2. And from 2 to 8, we're adding 6. Now to go from 11 to 5, we are subtracting 6. To go from 5 to 2, we're subtracting 3. To go from 2 to negative 7, we're subtracting 9. Now notice, our changes are not constant here. The changes are changing. But that's not what matters. What matters is whether the rate of change is changing. And the rate of change is delta y, change in y, divided by change in x. So let's work out what these changes actually are. I'm going to label these with subscripts so we can tell that these are separate changes. So the first rate of change will be negative 6 divided by positive 4. Let's fix that up. That simplifies to negative 3 over 2. The second rate of change will be negative 3 over 2, which is, well, negative 3 over 2. And finally, the third rate of change will be negative 9 over 6, which simplifies to negative 3 over 2. Now, we kind of already knew this was the rate of change because we wrote our function as y equals mx plus b above, and that was our m, negative 3 over 2. We get the same rate of change over here. But if we just had a table and we didn't know what the rule was, this is what we'd do to check if it was a linear function. So we have a constant rate of change, which means the function is linear. Our last test. Let's see whether the graph shows a linear function. So we have our points in a table, which means it's easy enough for us to plot them. So we have -4, 11, which would be right here. Then we have 0, 5, which would be right here. We have 2, 2, which is right there. And then we have 8, -7, which is right there. Okay, so if this really is a linear function, we should be able to connect these with a straight line. And with my ruler, that is indeed what we find. I haven't ruled that exactly perfectly. Hopefully you'll do a little bit better. It's made a little tricky having to hold it on a linear function. So, the plot is a straight line, and we know the drill by now, which means the function is linear. Okay, so the same function in 3 different forms, and for each form we have a test that tells us it really is linear. Now don't get the idea that we have to do this for every single function. What you'll actually do is for the form that you're given, you'll use the test for that form. But I want you to see how we can do it for each form. So that's what we've done it like this. Now, without further ado, our next example. So this one has the rule y equals x squared. Now, what we want for linear is we want it to be written y equals mx plus b. That's not going to work, because y equals mx plus b means all we're doing to our input, x, is multiplying it by a constant and possibly adding a constant. Now, we can also subtract and divide by using reciprocals and negatives and stuff like that. But all we're doing is multiplying and adding. This means x times x, and x isn't a constant. So x is being multiplied by something that's not a constant. So no matter what we try, this can't be written y equals mx plus b. Okay, and in fact, anytime you have x to the power of something written like this, you've turned it into a function that is not linear, and you won't be able to write it as y equals mx plus b. So this is a nonlinear function. The function is non-linear. It's all about that power being on the x. It means it can't be linear no matter what we try. Okay, let's make a table for this function and see if that shows that it's also nonlinear. So all we're doing is taking the input and we're squaring it, so multiplying it by itself. So -3 times -3 is 9. -2 times -2 is 4. 1, 0, 1, 4, 9. And let's figure out the changes. To go from -3 to -2, we're adding 1. And in fact, all of these, unlike the last table, these are in fact adding 1. Let's look at the changes in y though. From 9 to 4, we're subtracting 5. From 4 to 1, we're subtracting 3. From 1 to 0, we're subtracting 1, and then we're adding 1, and then we're adding 3, and then we're adding 5. Well, we know that our rate of change is simply delta y over delta x. And for all of these, delta x is just 1. So it's just going to be delta y divided by 1, which is just the same as delta y. So our first rate of change is -5, and then it's -3, and then it's -1. And I hope you can see here, it's fairly clear right from the beginning that this is not a constant rate of change. The rate of change is itself changing. So the rate of change is changing, which means that the function is non-linear. Okay, one last example. So we're going to take the same function and we are going to plot it on the coordinate plane. So first coordinate was, can't quite see that anymore, -3, 9. So we've got -3 going up to 9, which is there. And we've got -2 going up to 4. Then we've got -1 going to 1, 0, 0, 1, 1, 2, 4, and 3, 9. And hopefully you can tell, without even pulling the ruler out, that's not a straight line. In fact, this is a little difficult to do without doing it with a pencil, so I'm going to do my best here. But this actually forms a kind of curved shape. So this is something called a parabola. You don't need to know that for this class, but it's something you'll learn much more in high school about this particular graph. In fact, you will learn a lot about this function in high school. For now, there's really only one thing we're interested in it though. So the plot is not a straight line, which, as we've seen, means the function is non-linear.